Welcome. This is Professor Hirentrada. In this video, we are going to look at PreLab 7, PreLab 7 for EE361. There are 5 questions in this PreLab. Let's see. So it's basically digital part 2, where we have counters, shift registers, memory, and application. So the first question asks to draw the complete timing diagram for the circuit shown in the figure, proving that it is a 10 counter. 10 counter. Okay. So let's look at the circuit first. We have 4 JK flip-flops, right? 4 JK flip-flops. And all 4 of them have their J and K inputs connected to high, noted by the 1 symbol next to both of them. Okay. If you look at the clock is actually negative edge triggered. So the bubble in there means it is negative edge triggered right here, meaning every time the clock signal goes from high to low is when you would have a transition. Now the JK flip-flop, of course, it has, depending on the 2 inputs, you can have different states. But when both J and K are connected to 1 or to logic high, then it is in a toggle mode. It's toggle mode, meaning the output will simply keep toggling between 0 and 1. So we see that the output of the first flip-flop goes as the clock input to the second one, and the output of the second one goes to the clock input of the third one, and then the third output goes to the clock input of the fourth one. And if you look down here, the clear signal is also a active low, meaning when the clear signal goes low, all of the memory of the flip-flops is cleared out and the outputs are reset to 0. Okay, that's what that bubble means. The small bubble on the outside of that frame indicates that it is a active low input. Now, the clear signal is actually connected to the NAND gate up here. And the NAND gate has its 2 inputs as Q1 and Q3. Okay, Q1 and Q3. So let's look at how we will solve for this circuit. So here I have created a simple replication. For obvious reasons, lack of space, I've just compressed the circuit schematic, and I've not shown all the inputs, just assumed that J and K are connected to 1, and I'm not showing those. So let's look at what a 10 counter is first. Okay, 10 counter. As the name suggests, it counts 10 digits or 10 numbers. The binary number system, everything starts from 0. So 0 is actually what we would say as our starting point as the number 1. Okay. And so a 10 counter would count from 0 to 9. Okay, 0 to 9, and then it should go back to 0. So in the binary number system, the least significant digit or least significant bit would be represented by Q0, and the most significant bit would be represented by Q3. So it's a 4-digit counter or a 4-bit counter. And in the binary number system, the first one is 0, 0, 0, 0, then 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, and 1, 0, 0, 1. That is 9. And when it goes from 9 to 1, 0, 1, 0, it should automatically reset to 0, 0, 0, 0. Okay, so let's analyze the circuit and see how it would work. So as I was saying, both the clock and the clear signals activate on the falling edge. And so on a negative going transition from high to low, meaning it has to go from 1 to 0 on the negative edge, that is when the JK flip-flop will toggle, it'll activate. Now, if we look at the NAND gate truth table tells us that the output of the NAND gate would go 0 only when both the inputs are 1. Both the inputs are 1, right? A NAND gate is basically the NOT of an AND gate, right? So when 1 times 1 gives you 1 and a NOT of 1 is 0. That's the only case where the output of the NAND gate would go to 0. So if we look at the truth table of the counter, the only case where both Q3 and Q1 go to high is right there, which would actually be the number 10, or representation of the decimal number 10, 1010. However, the transition begins when the outputs are 1001, and for a moment, it's a fraction of a second, near instantaneously, when it starts transitioning from 1001 to 1010, the NAND gate output goes low, and because the NAND gate output goes low, the counter resets. The clear signal is activated. The clear signal is activated. All of the flip-flops are cleared, and all are reset to 0, 0, 0, 0. Okay, 0, 0, 0, 0. That is how this circuit would function. Now, it's with regards to how the outputs would function, because you have to draw the timing diagram. So let me just explain how this would work. At the beginning, let's assume we are starting from 0, 0, 0, 0, right? So we have 4 zeros in Q3 to Q0. Now, the output of Q0 is fed as input to Q1, right? So let's say the first clock pulse arrives. The first negative clock pulse arrives. And the first negative clock pulse arrives, or falling edge, this Q0 goes to 1. Now this 1, meaning Q0 has now gone to high, is fed as input to Q1. But Q1 will not change until this transition takes place, meaning it goes from 1 to 0, right? And so the output of Q1 does not toggle, remains at 0, which is fed as input to Q2. That also remains 0, which is fed as input to Q3, which also remains as 0, right? Now, when the second clock pulse arrives, or the negative edge, this one goes to 0. And this is fed as input to Q1. And now we have a falling edge for Q1, right? The clock for Q1 is now going from it's going from 1 to 0, meaning it's a falling edge. And so now Q1 will toggle, and you get a 1. This is fed as input to Q3. However, it is a transition from low to high for the clock. So Q3 remains 0, Q2 remains 0, and hence Q3 also remains 0. The third clock pulse arrives. Well, I think by now you should have a good idea of what's going to happen. This goes to 1. This is fed as input here. However, it is a transition from low to high, so this will still remain 1. And because it is again a transition there's no transition from high to low, these two also remain the same. And so you can see we have 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. And then you should be able to draw out the timing diagram based on this truth table. Okay, based on the explanation here. Okay, let's look at question number 2. Question number 2, actually 2, 3, and 4, they're all similar. So question numbers 2, 3, and 4, they're all similar. They deal with a shift register. A shift register is basically a memory storage device that stores information as bits. And here we are told we have a shift right register with contents 1010. Okay, farthest to the left is the most significant bit. So let's see, solve for this. So we have a shift right register, and we have the initial storage as 1010. This is the most significant bit. This is the least significant bit. It's a 4-bit shift register. Now, the input is coming from the left. So all of the data is moving towards the right. This least significant bit is actually moved out. Okay. So anytime one clock pulse arrives, you have input being fed into this register. So the contents of the register keep shifting towards the right, and hence the name shift right register. We are told that the serial input data equals 1, meaning there are a series of ones that are being fed into with every clock pulse. So in the first clock pulse, one enters from the left, and so now my most significant bit is 1, and then this one moves here, 1 place towards the right. 0 moves here, and this 1 moves here. Right? It's a shift right register, so every input of 1 from the left is moving the data towards the right. And well, that's all there is to it. Now you can simulate what happens when the second clock pulse arrives and the third clock pulse arrives. All of the data just keep shifting towards the right, 1 bit at a time. And then you just determine what the contents are after 3 clock pulses, meaning 1, 2, and 3. Question number 3 is exactly the same. But now you have a shift left register. Okay, shift left register. 4 is again a shift left register. No, it's a shift right register. Shift right register. Shift right register. But the least significant bit is connected to the serial input. Okay. The least significant bit is connected to the serial input. So what do we have? We have 0, 1, 0, 1. This is the least significant bit. What is going to happen is shifting towards the right with every clock pulse, and the least significant bit goes into the most significant bit. Okay, so the serial input is coming from the left. So that's what it means. Now you simply, for every clock pulse, you simply write down what the data contents would be, and then determine the contents of the register after 3 clock pulses. And well, that's the answer. Question number 5 asks you about a parallel load. Well, as the name suggests, the data comes into the device in parallel. So here we all had series shift registers, right? Serial input. And so data comes in one by one. In a parallel, data lines are all at once, meaning if there are 4-bit devices, data is loaded all at once. Or data is transferred all at once by using 4 separate lines. Okay, 4 separate lines or 4 separate inputs. If it is a 2-bit device, then it has 2 inputs. If it is a 3-bit device, it has 3 inputs, and so on and so forth. Here, for instance, in questions 2, 3, and 4, we had a 4-bit device, but we only had one input. The data is entered serially, right? Serially, not parallel. Parallel would simply mean that, let's say, for instance, if we had 0, 1, 0, 1, then all of the data would be entered directly all at once into each bit individually. Okay, that is what a parallel load means. Well, and well, that's it for PreLab number 7. If you have any questions, please reach out to me, hstrada@calpoly.edu.